Welcome to the third video for our discussion of NMR. In this video, we'll continue to look at NMR spectra. We'll work a warm-up problem together to help you consolidate what you've learned about chemical shift and induction. And then we'll encounter the second of our major classes of information that we could use to gain structural information from an NMR spectrum itself. So let's get started with our warm-up problem. Given the structure on the slide, which has color-coded hydrogens, I just want you to decide which signal on the NMR spectrum that's on your screen actually comes from the red hydrogen. So do what you need to do to answer this question, and then we'll come back together. Okay, so here are the assignments for the signals. You can see that the hydrogen that's down, or the signal that's downfield at around 8 ppm is the red hydrogen, and then the signal at around 3.7 ppm corresponds to the blue hydrogens. So how could we rationalize this assignment? Well, what you probably did was to think about electron density, and that's great. That's more or less what I wanted you to do. The red hydrogen is going to experience more inductive withdrawal of electron density because it's close to 2 oxygens. Right? So if we actually counted bonds from the red hydrogen to either of the 2 oxygens, we just have to go across 2 bonds, right? The H to the C and then the C to NO. If we actually did the same analysis for the blue hydrogens, we find that we're close to one of the oxygens, but much further from the other. And so since we know induction is both related to what we're going to call distance, and also this concept of additivity, being closer to the 2 groups that are influencing things will actually make a hydrogen more electron poor, and therefore its chemical shift larger. So there would be another way to approach this as well, where we didn't use electron density at all. We could look at the intensities, or heights, I guess, of these signals, right? And because we know that there are 3 blue hydrogens and just 1 red hydrogen, the larger signal might correspond to the blue hydrogen. So it kind of makes some intuitive sense. And it turns out that that's actually true. So if you were to do a little bit of calculus and not measure the height of the peaks, which turns out not to be very reliable, but rather the area under them, or essentially the area under the curve that is these peaks, and that's sounding a little familiar already, that will correspond to essentially the number of hydrogens giving that signal. As we'll see later in this video, that's not exactly what's called an integration value means, but that's more or less the information we gain from these so-called integration values. So again, please do not look at peak heights, right? You'll always be given the integration values, which you would obtain from processing the NMR spectrum on like a computer. So we can see that the integration for the signal at 8 ppm is 1, which might correspond to 1 hydrogen, whereas the signal at 3.7 has an integration of 3, which might correspond to 3 hydrogens. Okay, so roughly speaking, we can say integration is a count of what we're going to call equivalent nuclei. So what we mean by equivalent is that NMR can't tell like 2 or more hydrogens apart from one another. They give exactly the same signal at the exact same chemical shift. And what ends up happening is, like, you imagine the signal gets stacked on top of another signal, and that signal gets bigger, which is what you're seeing here on the NMR spectrum. So we've kind of avoided this concept of a y-axis up to this point on these spectra. The y-axis is kind of like intensity, but we're going to use integration for figuring out like how many hydrogens are giving a particular signal. Well, as you might be able to guess, to be able to interpret integration or make any kinds of predictions, we need to be able to assess equivalency. So I did that for you for this molecule by coding all 3 of the hydrogens on the left-hand side of the molecule as blue, but maybe that wouldn't happen in a normal situation. Pro tip, it won't. So you would need to be able to decide, oh, all 3 of those hydrogens of the methyl group, those are all equivalent. So how do we do this? So first, a disclaimer, there is a formal method for doing this, which will always give you the answer you'll observe by NMR spectroscopy. It's fairly involved and requires a lot of use and understanding of symmetry. So if you're thinking you might be interested in doing organic chemistry research, or maybe NMR in the service of biochemistry, we can talk. I'm happy to teach this method to you, but please know that it will not be part of the class formally. We're going to learn some shortcuts. These will work for simple molecules, the kinds of things you would see in a homework assignment or an exam or the MCAT or in lab this semester. but really for only very simple molecules. Like once you start dealing with things that are more complex structurally, these rules will start to break down. So we'll start by kind of having a general concept here. Atoms that are in identical environments are equivalent in NMR. So what we mean is that like a hydrogen, for instance, or two different hydrogens, they experience the exact same influence from all of the neighboring groups, right? And if we have this equivalency, the signal will become more intense and the integration will go up. Okay, so we can parse this concept of identical environments or equivalency in three different, let's just call them rules. Some of these are will break down as compounds become more complex, and so you can see the asterisks on the rules that are impacted. So the first thing we can say is that all hydrogens attached to the same carbon are equivalent. So I'm showing you three examples where that would be true. The example on the left is the molecule we started the video with. The center molecule, we've got just a single carbon and two hydrogens attached. So since those two hydrogens are attached to the same carbon, we can say they're equivalent. And then finally, the example on the right, we can see the same thing. So there are more hydrogens than the ones that are coded as blue. I just wanted to pick two out of that compound. Those two H's are attached to the same carbon, and so we could say that they would have the same chemical shift, the exact same environment, and therefore they would give the same signal. Okay, so let's look at our second rule. This one's a little bit more complex, but you've actually thought about this at some level already. And that's to say that hydrogens across what's called an internal mirror plane. So essentially a place where you could cut the molecule in half and have two equal halves in a symmetrical molecule are equivalent. So these hydrogens that are across an internal mirror plane are equivalent to each other. So you can see three examples here. The mirror planes are shown with these red dotted lines. You saw this when you assessed mesostereochemistry last semester. So in the example on the left, we've got two hydrogens that are not attached to the same carbon, but they are in the exact same environment because of the symmetrical nature of the molecule, right? So those two blue hydrogens have the same proximity to the chlorines and the methyl groups, so they experience the same environments, right? This is really what symmetry means, is that like the two halves are of equal environments, right? So in the center molecule, you can see the same thing, right? So it's not just like alkanes where this is true. As long as there's an internal mirror plane, going directly across the mirror plane will show you equivalent groups. And then finally, we could look at the molecule on the right, which hopefully looks a little bit familiar. It was on the previous slide. So I've just drawn in some more hydrogens. So not only is it the case that the two hydrogens on the very far right are equivalent to each other because they're on the same carbon, because this compound has an internal mirror plane, the two hydrogens to the left of that mirror plane are also equivalent. So another way of saying that is that in the structure on the far right with the two oxygens, there are actually four hydrogens, the ones I've drawn. Those are all equivalent to each other. So they're all going to give a single signal with an integration of 4. So I just want to be clear that structures can have more than one mirror plane. So the examples that I'm showing you here, they all just have one mirror plane that we care about anyway. But if you have like more than one mirror plane, you'll have to assess each of those equivalencies separately, okay? So the third rule is a little bit harder to parse or put into effect, and so this will take a little bit of practice on your part, and that's that you can look at whether or not hydrogens have like literally the exact same relationship to their neighbors. So we have one example on the far left, the blue hydrogens on those two methyl groups, right? Those are equivalent to each other because all 6 of those hydrogens have the exact same relationship to the bromine, to the iodine, to the CH2 group on the left, all that stuff. And so we could say that those methyl groups are going to appear to be equivalent by NMR. So all 6 of them will give the exact same signal, and that signal will have an integration of, like, let's say 6. But you can also see a couple of cases where this concept of exactly the same relationship doesn't apply. So I picked these because they're common misconceptions that I see when I teach NMR. So if we compare for the center molecule, the blue hydrogens to the red hydrogens, they're both methyl groups. And that might be like, well, methyl groups all have the same signal. No, they don't, because the blue hydrogens are like closer to the bromine and further from the iodine, whereas the red hydrogens are like closer to the iodine and further from the bromine. So they're in different relationships or different distances to the neighboring groups, right? So the red and the blue hydrogens, they're not equivalent. I would have one signal for all 3 blue hydrogens integrated into 3, and and I'd have a different signal for all 3 hydrogens that are red integrated into 3. So the molecule on the right, we also have this problem where we don't have exactly the same relationships to neighboring groups. So the blue hydrogens are equivalent to each other. They're attached to the same carbon. And the red hydrogens are equivalent to each other. They're attached to the same carbon. But the blue and the red hydrogens are not equivalent to each other. The difference is subtle. You look at the, oh, well, they're both next to oxygen, like what's the big deal? Well, even the presence of like a methyl group on one side and an ethyl group on the other side of those 2 ethers is enough to make these environments different. And so these signals will be different. They do not have the exact same relationship to their neighbors. So you have to be very careful how you look at this. It's not enough to just say, oh, like I'm near an oxygen, count it. You really need to be careful about traveling far away from the atoms you're assessing. More than maybe any other part of organic chemistry, NMR requires precision and thoroughness. Okay, so why is this helpful for us? Well, we've already talked about integration. The other thing that we can use our assessment of equivalency for is to decide how many signals in an NMR spectrum we ought to see. So maybe we already know a structure, and we're trying to decide, does that NMR spectrum match the structure? Again, that would be common in a laboratory environment where you think you know what you made, and you're trying to decide, did you actually make it? So the number of unique hydrogens, right? So basically another way of saying that is like how many types of hydrogens rather than how many total hydrogens. It's always going to be equal to the number of signals in the NMR spectrum. So let's actually take all of what we've discussed with respect to equivalency and work a practice problem together. So you can see the structure on the right. What I'd like for you to do is basically make a sketch of the proton NMR spectrum for the compound. But to do this, I want you to answer 3 questions independently before you start to draw. First, I want you to decide how many signals there will be. 9, 1, you have to decide. I just want you to decide relative chemical shifts, so I don't want you to pick a number. I want you to decide which signals are downfield from the others, and that means you'll have to make assignments. So for the hydrogens that you think are giving a specific signal, like which one are they on your sketch? And then I want you to actually write the integration for each of the signals, right? So basically, we need a number for the integration, some relative chemical shifts, like upfield, downfield, and then the number of total signals, right? So pause your video, answer these 3 questions, and then make your sketch. Okay, so you've had a chance to sketch. And rather than show you the NMR spectrum for this compound, the first thing I'm going to show you are the mirror planes, because what I'm trying to do initially with this concept of number of signals is decide where I have equivalent hydrogens. So if I look at the hydrogens on the ring, then I notice that, well, it looks like the top 2, those are equivalent to each other because I've got this vertical mirror plane. That's the vertical red line. But those hydrogens are equivalent to the hydrogens on the bottom of the ring because of the horizontal mirror plane. So this is an example where I have more than one mirror plane, and that's actually going to influence the equivalency in this molecule. So all 4 hydrogens on the ring are equivalent to each other. That also makes sense with respect to our third rule of equivalency in that they all have the exact same relationship to neighboring groups. They're all going to be ortho to a methyl group and meta to the other methyl group. So we have this kind of concept of where the rules reinforce each other. If we're using them correctly, they should be internally consistent with respect to each other. So we could also look at the methyl groups. The vertical mirror plane makes the 2 methyl groups equal to each other. We could also use the third rule, right? They are going to be equivalent because they have the exact same relationship to their neighbors. They're all going to be right next door or adjacent to the benzene ring. Okay, so it looks to me like we've just got 2 signals, right? All of the protons on the ring and then all of the protons on the methyl groups, plural. We can then think about relative chemical shifts. I've got protons attached to the aromatic ring, so those should appear in the aromatic region, somewhere between 6.5 and 8.5 ppm. And then the hydrogens attached to the methyl groups, those should be in the alkane region, somewhere between 4.5 and 0.5 ppm. So finally, I can look at integration. It looks to me like I've got 4 protons on the aromatic ring, so that signal in the aromatic region should integrate to 4. And the methyl groups, right, the hydrogens and the methyls, that signal in the alkane region should integrate to 6. So I'm just counting the hydrogens that are all equivalent to each other here. And this is the actual NMR spectrum of the compound. We do see 2 signals, just like we predicted. We have a signal in the aromatic region, almost right, exactly at 7 ppm. which is pretty common. Mostly we're close to 7 ppm or a little bit higher for benzene rings. And then in the alkane region, we've got a signal which appears to be taller, but we really need the integration values to know for sure. So at least for our first two predictions, the number of signals and relative chemical shifts are doing well. If we actually calculate the integration values, we find what we predicted. The integration for the signal in the aromatic region is 4. The integration for the signal in the alkane region is 6. But those numbers may be reported differently. Integration values are always relative. And it's really the ratio of integration values that indicates physical meaning, right? So we know that we've got 4 aromatic hydrogens for every 6 alkane hydrogens, but we could express that ratio 4 to 6 in different ways, right? We could say that we've got like the equivalent of like 1 aromatic hydrogen, in which case we would have 1.5 alkane hydrogens, or we could say we've got 2 aromatic hydrogens and 3 alkane hydrogens, right? So just remember that when you see integration values, they will not always actually end up being like counts of hydrogens, right? It's the ratios that tell you how much of one kind of hydrogen you have to the other. I'll do my best to always provide integration or spectra that have integration that does correspond to true counts of hydrogen atoms, but I can't guarantee that that will happen in lab this semester or in practice problems that you see in the various resources pointed out in the SLO documents. So just be aware of this property of integration values. Okay, so let's look at a slightly different kind of assessment here, and we'll think about the impact of conformation. So you learned about conformations of rings and alkanes last semester, so you learned about Newman projections and gauche interactions and chairs and chair flips and all that stuff, right? It turns out that's going to be relevant for us here too. So what I've drawn is cyclohexane, but I've drawn it as a chair, and I'm showing you, I've just drawn 2 of the 12 hydrogens that exist in the compound. And you know that one of the hydrogens is axial, and one of them is equatorial. So what I want you to decide is how many unique hydrogens there are in cyclohexane. And then once you've done that, I want you to predict how many signals you'll see in the proton NMR spectrum of cyclohexane. So pause your video, make your 2 predictions now. All right, so you've had a chance to think this through. My guess is that you probably came up with one of 2 answers, which is actually kind of a pun, because I think that you probably either decided that there are 2 unique hydrogens here, so the axial and the equatorial, or you may have decided that you have 1 unique hydrogen because, like, hey, those hydrogens are attached to the same carbon. So this seems to be a place where Rule 1 and Rule 3 are opposed to one another. Right? Rule 1 tells me that every hydrogen that's actually attached to the same carbon is equivalent. Rule 3 tells me I need to be in the exact same environment to be equivalent. So, well, Rule 3 says these should be different. Axial and equatorial are different environments in the sense that, like, with the hydrogens either point straight up or kind of out from the ring. So how do we decide this? Well, we look at data. We would actually acquire the NMR spectrum here, and we find just a single signal, which is surprising. So it turns out that conformational changes are way faster than an NMR can acquire information. So if you've ever thought about how a camera works, or especially an older camera, like a mechanical one, you basically have film and then you open a little hole in front of the film. The light goes through the hole and hits the film, and that's what you actually end up kind of taking a picture of, is the light going through there. So as long as that hole is open, light's going in and the film is developing. So if you imagine taking a picture of someone who's running really fast, it looks blurry, right? Because you basically are collecting light from that person that's over multiple positions of that person's body as they run. And so this blurring, you're averaging all of the different states of that person over the time frame where that hole in the camera was open. NMR is the same way. It actually has its hole open essentially for about 1 second, which sounds fast, but it's an eternity for a molecule. So this cyclohexane has done, like, this could be wrong, but maybe not too much of an exaggeration, millions of ring flips in 1 second. And so half the time a hydrogen that's axial is actually equatorial, and that averages out to a single position. So Rule 1 of equivalency really comes from this property, that, like, in most compounds, because we have bonds that are freely rotating or rings that are flipping, we have this averaging out to equivalency of hydrogens that are on the same carbon. But for complex molecules, and especially molecules with stereocenters, this doesn't always work out. So that's why we have that asterisk on rule 1, where it's like in more complex structures, it sometimes breaks down. So just do be aware that conformation matters. And there's a cool way you can actually test this, which is a little bit of an aside, but I think it's interesting. And that's that if you actually took cyclohexane as a sample and cooled it way down, so really low temperatures, like almost absolute zero, the rate of ring flip will drop dramatically. Basically, it doesn't happen anymore. It slows way down. And at that point, the NMR, it doesn't slow down. It still has its camera hole open for a second, essentially. You see two signals, right? Because the axial and equatorial, they are different environments. And those two hydrogens are actually distinct. So once you slow down the conformational change sufficiently, you actually see that those two hydrogens are not equivalent. All right, so I know this is a little bit of a complicating factor. Please still use rules 1 through 3, but I think this is also an important caveat, and it reinforces some of the things you learned last semester about conformation. All right, so that concludes our video about integration and equivalency. We've only got one more big piece of structural information derived from spectral data to go, and then we'll work some practice problems.